So what we're trying to do here is we're trying to find the capacitance of a spherical capacitor. Here we have a conducting sphere of radius A surrounded concentrically by a conducting spherical shell of inner radius B. So first, what we're trying to do is get it into this equation. We want to solve for the capacitance by knowing the charge and the potential. Now first off, we can solve for the electric field for a sphere that like we've done before. Again, we're going to use Gauss's law. And we're going to say that our electric field is the same everywhere. So it's a constant. I can pull that out of my integral. And then my area, I know, is changing by 4 pi r squared. That's the surface area of a sphere. Again, we've seen this calculation quite a few times before. So my electric field is simply Q enclosed over 4 pi r squared epsilon naught. Or if you wanted to simplify this, this would just be KQ over r squared. Now we said if this is our electric field, then we can solve for potential by getting the negative integral of my electric field with respect to position. So that means if I use this as my electric field, again, my charge enclosed is just Q in this case. So I'm going to go ahead and replace that with a Q. Again, that's my electric field. I'm taking the integral with respect to r. Everything is a constant, so I can pull that out of my integral. Everything except 1 over r squared. Again, the integral of 1 over r squared is negative 1 over r. So my negatives here are going to cancel out. And I'm going to integrate with respect to r. So I'm going to start with my radius a and go all the way until my radius r. So that becomes Q 4 pi epsilon naught 1 over r minus 1 over a. So now what I'm going to do here is I'm going to pull out a negative so this looks a little cleaner. Okay. The reason that I'm pulling out a negative is because looking at this, you can't tell that you're going to get a negative in this fraction, in this parentheses right here. But if a is greater, or if r is greater than a, then you will get a negative number. So I'm going to go ahead and pull that negative out. And that just means that we are going to have 1 over a minus 1 over r. Okay. Again, you can distribute that negative again to make sure that you are getting the same answer. So now if you look at inside this parentheses, it doesn't matter what r is, as long as r is greater than a, we will get a positive number inside of my parentheses. Now this makes sense, because if our potential difference between a positive charge and negative charge, we know our potential decreases as we move from positive to negative. It makes sense that we should get a negative value. But again, all we're concerned about are magnitudes here. So that means that our potential difference is going to be Q over 4 pi epsilon naught 1 over a minus 1 over r. Now we're going to clean this up a little bit with some more algebra. Okay. Here I'm going to set r equal to b because we want to know specifically the potential between a and b. So I'm going to go ahead and replace r with b. And now I'm going to clean this up. That means I need to multiply this by b. Okay. So really I'm multiplying it by 1, which is b over b. And then I'm going to multiply the second fraction with a over a. So that I get b minus a over ab. Again, this is the magnitude of our potential difference. Now our potential is going to go here in V. So if I wanted to solve for capacitance, I simply plug in my potential. Again, this is just a lot of algebra. Here you're going to notice that my q's will cancel out. And if I have b minus a down at the bottom, you're going to end up with, again, this is being multiplied. So you're going to end up with 4 pi epsilon naught a b all over b minus a. And this is our capacitance for spherical capacitors. Here we're going to solve for the cylindrical capacitance. So we're going to apply the same principles that we did before. First, solving for the electric field, then taking the integral and solving for potential, and then plugging that into our C equals Q over V equation. So, starting with Gauss's law. Again, we've done all these before, so I'm going through them a little quick. Okay, so we're trying to solve for the potential between A and B. So first off, I want to solve for my electric field between A and B. Again, it's going to be a constant, so I'm going to pull that out. My area, in this case, is a cylinder, but we're seeing a side view, so this is 2 pi r L. My charge enclosed, in this case, is positive Q. And then we have epsilon naught. So my electric field is equal to Q over 2 pi r L epsilon naught. And when we first did this derivation, we said that lambda was equal to Q over L, so we made that substitution also. So I can go ahead and do that now and say that Q over L gives me lambda over 2 pi r epsilon naught. So again, this is my electric field between A and B. Okay. So now I'm going to solve for my potential, which is the negative integral of my electric field with respect to R. Plug this in for my electric field. Take out my constants. And then take the integral. So here, the integral of 1 over r is natural log of r. And again, I'm going to integrate it between A and B, because that's where I want to know my potential between. So my potential is negative lambda 2 pi r epsilon naught natural log of B minus a natural log of A, which just gives me the natural log of B over A. Now again, this is my potential difference. I know that my potential difference is decreasing as I go from Q to negative Q. So I'm just going to get the magnitude and say that my potential is equal to lambda 2 pi r epsilon naught natural log of B over A. Again, I'm going to use this equation and put it into my capacitance equation. I'm going to go ahead and put Q over L back in for lambda. And then L goes back in. I have the natural log of B over A up on top. So here my Q's will cancel, and I'm left with 2 pi r epsilon naught L over the natural log of B over A. So again, this is my capacitance for a cylindrical capacitor. Finally, the capacitance of an isolated charged sphere is not very common, but it is possible. So again, while the most common situation is that of two conductors, a single conductor also has a capacitance. For example, imagine a spherical charged conductor. The electric field lines around the conductor are exactly the same as if it were a conducting shell of infinite radius, concentric with the sphere, and carrying a charge of the same magnitude but opposite sign. Thus, we can identify the imaginary shell as the second conductor of a two-conductor capacitor. We now calculate the capacitance for this situation. remember that the electric potential of the sphere of radius r is simply kq over r, and setting v is equal to 0 for the infinitely large sphere. We have, again, our potential is kq over r. Q's will cancel, so we're left with r over k, or just simply 4 pi epsilon naught over r. Now again, this is not very common, but it is important that you've seen it before. And finally, our most common situation is a capacitance of two parallel plates. Now you already know the equation for it, which is k epsilon naught a over d, but we're going to go ahead and derive it. So again, for two parallel plates, what I need to do is solve for the electric field between them first. Again, starting with Gauss's law, we say the integral of E dA is equal to charged enclosed over epsilon naught. So what I'm going to do first is I'm going to look at Gauss's law for just one of the sheets. Okay, so I'm going to look at just one of the sheets, and I'm going to say that I have a shape, and now it can be any shape, but most commonly you'll see this as a cylinder. Now again, the electric field is going to be constant everywhere, so I can go ahead and pull that out of my integral, but my area is going to be 2 times my area. That means I have an area on this side of the sheet, and I have that same area on this side of the sheet. So I have 2 times that area. Again, my charge enclosed will just be the charge on the plate. So this gives me an electric field equal to Q over 2A epsilon naught. Now, there's one symbol that we've seen before but we hadn't used, which is sigma, which is the charge per unit area. Now we've seen lambda, which is charge per unit length. We've seen rho, which is charge per unit volume. But we hadn't talked about sigma yet. Now sigma is charge per unit area. Now here I have a charge per unit area, so I'm going to replace that with a sigma. So this is the electric field for just one of the sheets. So if I want to have 2 of the sheets, I can simply add them together. This is going to be the electric field in between the sheets, and then outside of the sheets on this side. And this side, we're not going to have an electric field. Okay, so when I add those 2 together, my electric field for the plates is simply this times 2. So I get sigma over epsilon naught is my electric field in between these 2 plates. So to solve for the potential, it's simply negative integral of E dr, where E is now sigma epsilon naught. When I take the integral of that, that gives me sigma r over epsilon naught, where r in this case is representing the distance in between these 2 plates. Another way to say that is 0 to d. So I get negative epsilon d over, sigma over epsilon naught. Again, this is my potential. We already know that my potential difference decreases if one plate is positive and the other one is negative, and we go from positive to negative. So again, the magnitude of it is just sigma. I'm going to go ahead and put my charge over area back. And again, I'm trying to solve for the capacitance. So I put Q over D over epsilon A. Again, my Q's cancel out, and I'm left with epsilon naught A over D, which again, we've already seen is a capacitance of parallel plates.